Hey everybody, today we're going to be looking at global winds. I'm not talking about the breezes and winds that you feel in your backyard or when you're sitting on the beach. I'm talking about really huge, large, earth-size wind patterns that happen at certain areas of the earth. So we're going to take a look at that. So what I'm going to get you to do with me today is to do some drawing with me. If you can draw along with me. If you need to, you can stop the video at any time. You can back it up. You are in charge of how fast or slow I go for you. So with this video. So the first thing you need to do and make sure that you get, if you saw the announcement and saw the assignment, you're going to need a piece of paper, whether it's white paper, notebook paper, colored paper, doesn't matter to me. It'll just be something that we're going to add into our notebook. So stop the video here, grab a piece of paper and a pencil, and then come back and get ready to follow my drawings. Okay, so to focus on our global wind patterns, those really big Earth-sized wind patterns, we have to kind of remember back to when we talked about Earth processes. We were talking about the Earth, how it moves, we talked about the seasons and everything else. One of the things that we looked at was there were certain areas of the Earth that were very important that I wanted you to remember because they were going to make a difference when we looked at our seasons and we looked at sun and everything else and how much the sun hits the earth and all. So if this is my earth right here, I'm going to do I drew a semicircle right here. It's kind of a semicircle on the left side of my paper. Go ahead and draw that there. Doesn't make any difference if it's perfect. If it looks like a half of a potato, it's not a big deal. This is for you. Okay, so here's our semicircle that we drew, and that's going to be, we're going to be looking at our earth, and over here we've got a bigger circle that's going to be our sun. So we're going to be looking at the sun. And so on the earth, we talked about those locations. And one of the locations was that imaginary line that cuts the earth right in half, separating the northern hemisphere from the southern hemisphere, right? Northern and southern hemispheres. So we're looking at those. And on here, we then said, here's that halfway point. And then halfway up in the northern hemisphere, we had that mark that was the Tropic of Cancer, and then of course down here in the southern hemisphere it was the Tropic of Capricorn. That's at the 45-degree latitude mark. Tropic of Cancer, 45-degree north latitude. Tropic of Capricorn, 45-degree south latitude. These are all latitudes. Latitudes. Think about latitudes run east and west. They measure north to south, but they run east to west, so they're flat. So think latitude, latitude. Okay? So latitude, latitude. All right, let me get my paper back here. Yeah? All right. So we're not going to look at the 45 degree. We want to look at a couple of them a little bit above the equator there. We have a 30-degree north latitude. Then we have a 60-degree north latitude. Then we have at the poles a 90-degree north latitude. And of course, if it's this way in the north, you know it's going to be the opposite way in the south. So here we're going to have a 30-degree south latitude, then a 60-degree south latitude, and then down here at the poles we have a 90-degree south latitude. So we're looking at that. On any maps you can begin to find things by looking at their latitudes, finding the latitudes. Okay, now when we're looking at this, we have to think about all the energy and everything else. We know when we did our solar unit and we did our solar ovens and everything else and we cooked our marshmallows, we had our solar unit, and The sun is the source of heat and energy that comes to the earth. And so here we have this heat and energy that's going to come right here towards the earth. We have the sun, and on the sun we have our corona. No, it's not the virus. No, it's not the beer. We have the corona, so that's kind of like the rays that are coming out, the glow that's around it. And solar energy comes out as light energy. Comes out as light energy. So it has, it's got that visible light spectrum in the very center of the electromagnetic spectrum, if you remember what we're talking about. So that light energy is very linear, okay? This is the solar energy is light energy. And light is linear. Light is linear. And what that means is that linear means a straight line. Straight line. Straight line. Okay? Straight line. So all this light energy is coming straight at the earth. It's coming straight down right at the earth. Okay? And it comes straight out. If I had trying to draw straight lines here, all that kind of good stuff. Okay? So if it comes here towards now, we know that the light is consistent here at the equator, that consistently throughout the entire year, we saw that it gets 12 hours of light, 12 hours of darkness, every season, every day, all year long. So the light is very consistent. One of the reasons is that linear light that's coming straight in right here, if I were to look at the angle of it, it would make a 90-degree angle. It would make a 90-degree angle. So that was what's called a direct ray. So very direct ray. Here, as I go through and I kind of look at the different areas of the earth, and I bring light in, and it reaches the different levels of the earth, because the earth is curved, it begins to have a very different angle to it. Check out these angles as they change. If I bring another light in here from the earth, above here, look at that angle, that it definitely changes. So the angle begins to get smaller and smaller as it gets to the 90 degree. If you got a compass or a protractor and you checked what your protractor said the angle was, those angles would become less and less. They would be less than 90 degrees. Here is an indirect ray. These are indirect lights. So you're not getting really direct light. So it's like if you were sitting on the face of the earth and it was indirect, and I'm standing here on the surface of the earth, standing on the surface of the earth, and I have direct and indirect rays coming at me, I'm going to have very indirect rays like this. They're going to come in at an angle, where a direct ray is going to come straight down like this. Think about this. During the day, when is the most heat of the day? As they call it, when's the heat of the day? And that's usually when the sun is straight overhead. It's around between 10 o'clock and 2 o'clock, you're getting the most sun, you get the most sunburn, because you're getting the most direct rays. As it kind of goes around, as we're turning and rotating around, those direct rays are going to come in. And that's going to be a lot cooler, like early in the morning, later at night, about sunrise, sunset. It's going to be cooler. So these indirect rays that are coming in here at the poles are going to be indirect. If I could spell, indirect. These are going to be much cooler. The direct rays are going to be hotter. Okay? So that kind of makes sense. You've known this for a long time. At the equator, that's where we're going to get our most warm temperatures. Here at the poles are where we get our colder temperatures. We have our polar bears. We have our, the Antarctic, the Arctic and the Antarctic are almost, unlivable because of such cold, cold temperatures. Here is where we have at the equator, we have all that warm weather. Okay? So this is all because of the indirect and direct heating or direct light reaching the earth. Now what that ends up causing is let me slide this up just a little bit for you. Okay? What that causes is uneven surface temperatures. Okay? That means that it's going to be much warmer here than it is here and much colder here. Really hot here, warm here, and cold here. Very uneven surface temperatures, right? Very uneven surface temperatures. Those uneven surface temperatures cause convection cells, okay? They cause convection cells on the earth. And because we have those convection cells, that causes pressure systems, and that's what's leading us into our weather and our climate. But today what we're going to be looking at here is mainly the uneven surface temperatures. It'd really be very helpful if I could actually spell here today, couldn't it? I told y'all, you can always count on me for two things. I will always help anybody who is willing to ask for help and get help, and I will always, always misspell something on the board. Well, welcome to my new board. Okay, so uneven surface temperatures, or you may hear it as uneven solar heating. But we're going to talk about the surface temperatures, okay? So uneven surface temperatures cause convection cells. So we're going to get in there and we're going to look at these convection cells really closely and take a look at them, okay? So you can either continue on with your piece of paper, or if you've got space and everything else, or if you drew really big on everything else, you can flip it over. Oh, I'm going to need a new piece. We're going to change that out to get a new piece. So I have a clean piece, or you can just turn yours over to where it's clean. Okay, and we're going to look at global winds. Okay, so here we go. We're going to say global winds. Okay, ooh, global winds. All right, so in looking at this, we have our Earth. Okay, we're going to draw a big old Earth here. Now, it doesn't have to be perfect, remember? It can look like a big old potato if you need it to, as long as you're getting it. So go ahead and get your Earth in there. Again, that imaginary line that cuts it right in half, that is the 0 degrees latitude. So now I have the northern hemisphere and the southern hemisphere. I'm going to look at 30 degrees north latitude and 60 degrees north latitude, and then 90 degrees north latitude. Same thing down here in the southern hemisphere. 30 degrees south latitude, 60 degrees south latitude, and then 90 degrees south latitude. Okay? Now, we're looking at convection currents. Okay? So, when we looked at the atmosphere, and when you were studying and looking at the atmosphere, we said Tricky Spider-Man took Elmo. And that very first layer of the atmosphere, the one that's closest to the Earth's surface, the troposphere, is where all of our weather takes place. So if I'm looking at the Earth's surface here, So let's say this is my Earth's surface. Okay, here's my Earth's surface. And you know that when those direct rays come in, they start to warm up the Earth's surface. So it's going to start warming it up. Well, in here above the Earth's surface is all this air, air in the atmosphere. Okay? So we know that when air begins to heat up, and we saw this with our balloon, we saw it with all of the different amazing air demonstrations and activities that we did. We know that air, when it heats up, it becomes less dense and it starts to rise up. So warm air is less dense and it rises. Okay? Warm air, less dense, it rises. Well, now it's up here at the higher altitude. It's going up in the higher altitude. It's getting farther and farther away from this warm Earth surface. Kind of like when you are at a campfire and you go walking backwards, you get away from that campfire, it starts to become cooler. So the air moves up here, and as it gets up here to this higher altitude, so we have a high altitude, it starts to cool, right? It starts to cool off. And then as it starts to cool off, it becomes more dense. That air becomes more dense. And it comes back around down here and it begins to sink down towards the surface of the earth. Well, it doesn't go crashing into the surface of the earth. It actually gets closer. It's kind of like when you're walking towards that fire, that campfire. You start feeling the heat. You start feeling the warmth. You start warming up. So that air does the same thing, and it kind of moves right across the Earth's surface, and it warms up as it moves across the Earth's surface. Heard Miss Lang or Miss Winstead, whichever you want to call her, I've heard her say it whooshes across the Earth's surface. Well, it kind of just kind of moves across the Earth's surface, and it starts to warm up, and it becomes less dense, and it rises, and it hits a high altitude, so it starts to cool off, becomes more dense, and it sinks down, and then it whooshes across the Earth's surface, as she says, moves across the Earth's surface, it starts to warm back up, rises, and it comes up here at the high altitude, it cools, it's more dense, it sinks. So there we go, we get that convection current, right? We get a convection current or a cell of air that is constantly moving. So let me move this up a little bit so you can see what I just wrote. Convection current is moving here. Okay, so where here on Earth, what location do we know that it is warm all the time? Well, obviously, with those direct rays that are coming in, it's going to be the equator. The equator is going to be warm all the time. So that air over here, just right above the equator, all that air right in here, right above the equator, starts to warm and rise up, right? And as it moves away from that altitude, or it moves away from the surface, gets to that higher altitude, it starts to cool off. As it's up here at the higher altitude, it starts to cool off, becomes more dense, and it happens to do this right, that doesn't travel very far. It happens to do this right at this 30-degree latitude. And it starts to cool, it travels that far, all of the heat kind of dissipates off as it's at higher altitude, cools off, it becomes more dense, and it begins to sink. Again, doesn't crash into the surface, it kind of moves across the surface of the earth, warms up, and we get a cell of air. It's an interesting phenomenon that it happens right here at that 30-degree mark. So we get this equatorial cell of warm air rising, moving across being cool, coming back down, and continuing on. Warm air rises, more dense, cool air sinks, warm air, less dense, rises, cool air, more dense, sinks, warm air, less dense, rises, cool air, more dense, sinks. Well, if it's happening in the northern hemisphere, it's happening in the southern hemisphere. So it's kind of following right along here in the opposite direction. Here we got that warm air right at the equator coming up, gets into higher altitudes. Remember, this is the surface of the Earth coming up here to the higher altitudes. Starts to cool off here, becomes more dense, sinks, moves across the surface of the Earth and warms up, and we get these cells going in here. Same thing. Warm air, less dense, rises. Cool air, more dense, sinks. And it starts to displace everything and move in a convection current. Right? So this is the warmest area on Earth. That's consistently the warmest area. Let's look at these cooler areas. Okay? Much cooler areas. All right. So as this cool area is coming up, as this cool area here, we have this cool area. It's going to come down this direction. And as it moves across the Earth, it's going to be moving across the Earth's surface, and it's going to start to warm up. Now, I didn't say hot, nowhere near like this, but it's going to be warmer here than it is here. So that air right here about the 60-degree mark is going to come rising up because it's warmer here, gets higher in those altitudes, kind of comes across as it starts to cool, and of course you know that when it cools it's more dense and it comes down and then it'll come back across. So you get a cell up here at the poles. It's going to be cool air moving across, and cold air moving across the surface, warming up, warming, not hot, warming, more warm here than it is there. That will start to rise, and it'll cool with the altitude and come back down at the poles, and it'll begin to keep going in this direction like this as a convection cell. Same thing happening here. I got the cool air coming across the Earth, right? It'll start to warm up, okay? As it hits that high altitude, it's going to cool, it's going to become more dense, and it will sink back down to the Earth, come across. Really cold here, warmer here. Really cold and through here, warmer as it goes to that lower latitude. Okay. Well, now we got these areas right in here. We kind of call these the copycat cells. These are the copycat cells. They kind of bind up and they become friends and they take a walk with, or whatever you want to say, the air here. So if this air is coming down in this direction, the air here is also going to be coming down in this direction. But it doesn't go in this, this one's coming this direction. This one's going to go off across the Earth this way. And then it's going to run into, right about here at the 60-degree mark, it's going to run into this this air here. It's cooler than down here. They're going to run into this air, and it's going to kind of grab us. It's going to take a walk with it. And as it comes up to the higher altitudes, it cools off and it becomes down and it mixes in with this one, and they take a walk and they come down towards the surface of the Earth. And then they come up here. So it's copycatting whatever it is on these other cells. Well, what's really interesting about this is about where, the United States, North Carolina is going to be right around in this area. So this is a very important cell to our weather. And it's kind of the one that drives everything. These two airs come this way. These arrows are pulling air this direction. These stuff are going that way and this way. And then they meet up here and pull air back up this direction. And the altitude cools it and it continues to go. So as we can see here, the same thing's going to happen here in the southern hemisphere. It's going to take a walk with this particular cell. And it's going to go across the Earth's surface. It's going to, hit it. It's going to come across the Earth's surface. It's going to begin to then run into this cell, and it's going to be pushed up with that cell. Higher altitude, come back around this way, and begin to sink back down as it runs into this one. Now, the temperature thing kind of makes you go, wait a minute, that seems backwards. So just think about it as that this and this is the copycat cell. Okay, they're going to walk with here, spread apart, walk back down here. And this one kind of joins together with this air, splits apart, joins together with this air coming back down. So that's what they have there. These are what are called the polar cells. These are polar cells right down here. Okay. These are the feral cells. So these are feral cells. They're called feral from the scientists that identified them. And then these are called the Hadley cells. Hadley cells, also known by the scientist that identifies them. The polar cells, no, it wasn't Dr. Polar. These are the polar cells because it's at the poles. So polar, feral, and Hadley. And one way that I always try to remember how to do polar, Hadley, and polar, feral, and Hadley. So if I'm up here at the poles and I'm walking from the pole down to the equator, if I walk from the poles down to the equator, I'm going to hit the polar, then the feral, then the Hadley, right? And as I'm walking, it's going to get pretty flipping hot. PFH, pretty flipping hot, polar, feral, Hadley, because it's really cold up here and it's really warm down there. So as I'm moving downward, it's going to get pretty flipping hot. Okay, so what I need for you to do with this is hang on to these particular notes and all, because we're going to build on this. We're going to move into the climate, and then we're going to look at local winds, and we're going to talk about weather and weather maps. But this is just a really large scale, the way that you will see patterns as we go through all of these particular types of winds and all. And these are the cells that we have: polar cells, feral cell, Hadley cell, as they go from the poles down to the equator. If you can kind of keep that convection current in your mind, that warm air rises because it's less dense, gets to higher altitudes, cools off, becomes more dense and sinks, comes across the Earth's surface and heats back up and keeps right on going. Okay? And then we know that we have it, it's very different because we have that uneven surface temperatures, and we have that because of indirect rays and direct rays because light is linear and solar energy is light energy. And that uneven surface temperature causes our convection cells. And then we're going to move that into pressure systems, climate, and weather. Okay? If you guys have any questions, send me a text, send me an email. Let me know that you need to talk about this on Zoom or anything else. We can set up a one-on-one small group or something on Zoom. And you guys stay safe, stay healthy. I miss seeing you in class. And let me know if you need anything. I'm always here.